This study delves into the application of DINOv2, a deep learning-based method, in geological image analysis for classification, segmentation, and interpretability of CT scan images of rock samples. It compares various segmentation techniques, including Otsu thresholding, clustering methods, supervised machine learning approaches, and deep learning methods like UNet and DINOv2. The authors evaluate these methods using 10 binary sandstone datasets and 3 multi-class calcite datasets. In terms of interpretability, the authors provide a thorough analysis of DINOv2's features in the geoscientific context, highlighting its suitability for processing CT-scanned rock data. The out-of-the-box DINOv2 demonstrates an impressive capability to perfectly classify rock images, even when the CT scans are out of their original training set. Regarding segmentation, while fast thresholding and unsupervised methods perform poorly, supervised methods show better results. The authors highlight the computational demands of deep learning but emphasize its minimal intervention, superior generalization, and performance without additional image preprocessing. They also observe a lack of correlation between a network's depth or the number of parameters and its performance. The results show that a LoRA fine-tuned DINOv2 excels in out-of-distribution segmentation and significantly outperforms other methods in multi-class segmentation. The authors identify the most efficient strategy for meticulous and laborious segmentation tasks, with DINOv2 proving advantageous in achieving segmentations that could be described as better than ground truth against relatively small training sets. The study is motivated by the importance of advanced vision algorithms in understanding subsurface integrity for projects like CO2 storage. High-quality segmentation masks of CT-scanned rock volumes are crucial for petrophysical models, which accelerate the qualification of subsurface sites and ensure standardization across qualification studies. Image segmentation of micro-CT data is a crucial step in poor-scale modeling, but it remains a time-consuming and labor-intensive task. Machine learning and deep learning approaches have been employed to address this, but their development is hindered by the lack of publicly available multi-class datasets and the requirement for a substantial number of training samples. Foundation models, which can perform effectively with minimal data, have the potential to overcome this limitation. Despite their success in the medical field, foundation models have not been widely explored in geoscience applications. This study assesses the scalability of the DINOv2 foundation model for downstream applications in geoscience. The authors hypothesize that DINOv2 can be leveraged for accurate segmentation and classification, especially when faced with limited and noisy training data. To evaluate this, they compared DINOv2 with various baseline models and traditional segmentation techniques, including Otsu's method, K-means, fuzzy CM-means, random forest, and 2CNNs. The study highlights the need to utilize high-performing foundation models tuned to geoscientific data for segmentation and classification. DINOv2 significantly outperforms other popular segmentation methods, exhibiting superior generalizing capability with noisy and scarce data. Popular segmentation tools, including threshold-based and unsupervised segmentation techniques, are computationally efficient but often struggle with complex and noisy data. These techniques can be categorized into several families, each with its methodologies, use cases, advantages, and limitations. The authors demonstrate that DINOv2 can be effectively leveraged for accurate segmentation and classification, even with limited and noisy training data. This research aims to raise awareness amongst geoscientists about the potential of DINOv2 and provide empirical guidelines on how to best leverage it for geoscience applications. Nuanced segmentation is crucial in scan-type data and applications where boundary regions are ambiguous. To address this, two supervised techniques are introduced: an adaptation of the random forest (RF) algorithm and the UNet model. The RF algorithm is a versatile classification method that leverages an ensemble of decision trees to improve predictive accuracy and generalization. Each tree is trained on a different bootstrap sample of the data, with randomness in both sample selection and feature choice, ensuring diversity among trees and reducing the risk of overfitting. Predictions are made by aggregating the votes from all trees, with the majority vote determining the final class. The UNet architecture is a form of convolutional neural network, CNN, that can be used for image segmentation tasks. It consists of a contracting path, encoder, and an expansive path, decoder, capturing the context of the input image through multiple layers of convolutional operations and downsampling. Both RF and UNet have been successfully applied in various geoscientific fields, including SEM image segmentation and CT scanned rock segmentation. In addition, the DINOv2 foundation model is introduced, a large-scale, pre-trained model designed to serve as a versatile base for a wide range of downstream tasks. DINOv2 represents a state-of-the-art self-supervised learning method specifically designed for pre-training vision foundation models. It excels in creating robust image encoders by employing vision transformers, leveraging the attention mechanism to process images in a way that captures complex patterns and features. By pre-training this architecture on a vast and diverse dataset of images, DINOv2 generates visual features that are highly effective for various applications, such as image classification, object detection, and segmentation. The DINOv2 model, a versatile and robust foundation model, has been widely adopted in various domain-specific fields, including medical and geoscience, due to its adaptability and performance. In medical imaging, it has advanced the state-of-the-art in complex vision tasks, such as pathology, computational pathology, and semantic segmentation. However, despite its success in medical imaging, DINOv2 remains underutilized in geoscience, particularly for segmenting CT-scanned rock images. This presents an opportunity to leverage its capabilities for enhancing precision in rock segmentation, a pivotal task in the geoscientific community. Machine learning and deep learning approaches have been tested in geoscience, with the WECA tool from the Fiji software being widely used. Various UNet and CNN architectures have yielded satisfactory results, but fewer studies have attempted to adapt large foundation models for geoscientific segmentation tasks. Notably, only one study has utilized SAM for CT scanner segmentation, and no studies have been identified using DINOv2 for this purpose. To assess the potential benefits of DINOv2 in a geoscientific context, experiments were conducted using specific settings, including the data used, preprocessing pipeline, and significant hyperparameters. All experiments were run on an NVIDIA RTX 3060 and Tesla T4 GPU. The goal is to analyze and highlight the strengths and limitations of DINOv2 within the context of geological image analysis. A comprehensive probing and interpretability analysis of DINOv2's raw features is conducted to understand the model's innate suitability for the geoscience domain. The ability of a segmentation model leveraging DINOv2 to adapt to the application with minimal data is also investigated. Results are compared against those obtained with the state-of-the-art Universeg model to better contextualize the performance metric. The authors employed two distinct datasets in their study: the sandstones, set for classification tasks, and the carbonates, set for segmentation tasks. The carbonates dataset comprises 3 CT-scanned calcite core samples, each with a diameter of 4.8 mm and varying lengths, encompassing 3 classes: crude oil, brine, and rock matrix. The high granularity CT scans exhibit low overall contrast, making it challenging to discern fine details within the rock structure. In contrast, the sandstones dataset consists of 10 CT-scanned sandstone samples, each representing a different rock type with unique petromorphological characteristics. These CT scans exhibit a noticeable level of granularity, although less pronounced compared to those intended for segmentation purposes. To improve model robustness and generalization, the authors performed data augmentation using a transformation pipeline composed of random or center cropping, upsampling, random vertical or horizontal flips, contrast, brightness, and gamma adjustment. The optimal crop size and upsample resolution were determined through extensive trial and error. For machine learning and threshold-based methods, the authors denoised the data with a non-local mean filter to improve robustness. A hand-engineered basic feature extractor (BFE) was also employed to enhance some baseline machine learning algorithms, operating on denoised data and using a Gaussian kernel to compute 15-dimensional feature vectors. This feature extractor captures features at different levels of detail, adapting to the author's needs, as proposed in previous research. The study employs 3 DINOv2 model sizes: small, base, and large, with 22M, 86M, and 300M parameters, respectively, and feature vector sizes of 384, 768, and 1024. Input images are divided into fixed size, non-overlapping patches, transformed into feature vectors using DINOv2's vision transformer, and then processed by the backbone. To adapt large models to specific tasks efficiently, the study utilizes low-rank adaptation, LoRA, which freezes pre-trained model weights and injects trainable low-rank matrices into some layers, reducing the number of trainable parameters. In this study, the rank of the LoRA matrices is set to 32, and all linear layers, including attention matrices, are targeted. This approach reduces the number of trainable parameters, for instance, from 86M to 5M in DINOv2 base, resulting in substantial computational resource savings. Additionally, 4-bit quantization is implemented to further improve memory efficiency, reducing the numerical precision of the model weights and thereby greatly reducing the memory footprint and computational requirements while maintaining model performance. The study explores DINOv2's understanding of rock CT scans by leveraging existing probing and visualization methods to inspect whether DINOv2 can natively recognize and discriminate important petrophysical patterns. The experiments focus on 2 datasets with significantly different characteristics, and all experiments are run using a non-fine-tuned, frozen DINOv2 to highlight its intrinsic capabilities as a backbone for out-of-distribution data. To assess DINOv2 for rock type classification, the study visualizes DINOv2 base features when fed with data from the sandstones dataset using TSNE, which excels in dimensionality reduction and is particularly effective for visualizing high-dimensional data. The goal is to discover if scanned rocks sharing the same geological nature possess close latent representations in DINOv2's feature space, indicating a zero-shot geological pattern recognition ability. The capabilities of DINOv2 are further validated by training a k-nearest neighbors (KNN) model directly on top of the latent features to classify rock samples. The authors present their experimental results for the rock classification task using DINOv2 as a feature extractor. In Figure 1, the TSNE visualization of DINOv2's features demonstrates that scanners belonging to the same dataset, rock sample, are clustered together, with rock samples sharing similar characteristics also having close feature representations. This indicates that DINOv2 is sensitive to subtle but discriminating rock features despite not being trained on this domain. The authors also report on the performance of a KNN model for rock classification, finding that the results are largely stable with respect to the number of neighbors, K, and image resolution. Classification accuracy reaches 100% for most parameter settings, except at very low image resolutions, below 128 by 128, or very high values for K, above 100, where accuracy decreases to 96.5%. These findings validate the effectiveness of DINOv2 in extracting meaningful features for rock classification. Furthermore, the authors extend their previous findings by studying the performance of DINOv2 on a more challenging image segmentation task. They employ linear and KNN probing to analyze the segmentation capabilities of DINOv2. The authors' results suggest that DINOv2 can effectively capture relevant features for segmentation tasks, further supporting its versatility as a feature extractor. Evaluating feature quality through probing is crucial for multi-class image segmentation tasks. In the context of the carbonates dataset, this research employs DINOv2, a deep learning model, and compares its performance with a regular feature extractor, BFE. 2 probing methods are utilized: linear and KNN, commonly used in self-supervised learning to assess feature usefulness for downstream tasks. The experimental setup involves using DINOv2 small, DINOv2 base, and DINOv2 large to examine the correlation between feature size and downstream performance. Probing results on features extracted by BFE are also reported to highlight the benefits and superior quality of features learned by DINOv2. For linear probing, A simple segmentation head consisting of a single convolution layer with a 1x1 kernel and no padding is applied to predict class logits. For DINOv2, the 40x40 logits map is bilinearly upsampled to the full resolution, 560 by 560. A boosted version of the linear probing setup is also considered, where the patch tokens of the 4 last layers of the backbone are concatenated before the classifier. For KNN probing, the feature map is upsampled from the low-resolution 40x40 feature map to a higher resolution that matches the ground truth masks, ensuring a one-tune mapping between the training labels and feature vectors. To address computational complexity, DINOv2 features are upscaled from 40x40 to 128x128, and GT masks are downscaled from 224x224 to 128x128. The results of linear and KNN probing for multi-class image segmentation on the carbonates dataset are presented in Table 1. DINOv2 probing significantly outperforms the performance achieved using a regular feature extractor, indicating the essential contribution of DINOv2's powerful features to its success on the task. To understand why KNN works well with DINOv2 compared to BFE, TSNE visualization is used to comprehend the low-dimensional representation of each 128 by 128 feature vector for the same image and both approaches. The feature representation of the tested image under BFE appears more disorganized than DINOv2's, with BFE's pixel feature representation corresponding to the brine and rock matrix mostly blended and overlapping each other. In contrast, DINOv2's latent space contrasts the 3 classes more efficiently, leading to better probing results. The performance of segmentation models, DINOv2 and BFE, is evaluated on the test dataset using probing. As shown in Table 1, DINOv2 models outperform BFE, achieving higher intersection over union, IOU, scores. The TSNE visualization in Figure 2 illustrates the clustering of pixel-level feature vectors for a test image from sample S3, revealing that DINOv2 clusters are more distinct and well separated compared to BFE. Confusion matrices in Figure 3 provide further insight into segmentation predictions, where row indices represent true class labels and column indices represent predicted class labels. DINOv2's confusion matrix shows higher accuracy in predicting crude oil and rock matrix, with fewer misclassifications compared to BFE, indicating that DINOv2 models are more effective at separating the 3 components in the dataset. However, overlaps between some instances lead to confusion and misclassification of certain pixels, as seen in Figure 3a. This suggests that model refinement, such as adjusting the architecture or training parameters, could improve differentiation between components and achieve optimal performance. The evaluation highlights the strengths and limitations of the segmentation models, emphasizing the need for further refinement. The boosted linear probing setup, which processes the last 4 layers of DINOv2, significantly outperforms its 1-layer counterpart in the KNN classifier, particularly for DINOv2 small, with a notable increase of 0.117 IOU. This indicates that useful information is present in the intermediate layers, not only in the final layer. However, the performance gain from processing multiple layers decreases as the feature size increases, suggesting that higher dimensional features can intrinsically embed more information, making the addition of too many layers redundant. Furthermore, processing more features involves more computations, making the number of processed layers a trade-off between computation cost and performance. Linear probing achieves better IOU results than KNN, especially for large feature dimensions, greater than equals 768, which struggle with high-dimensional data. A simple linear classifier trained on top of frozen DINOv2 features achieves impressive results in a segmentation task compared to a hand-engineered baseline feature extractor, BFE. Moreover, DINOv2 shows remarkable robustness to noise compared to BFE-BASED models, which required an additional data denoising step. When fed with multi-layer features, it even approaches a fully supervised UNet model trained from scratch on this task and dataset. The TSNE visualization provides a means to interpret DINOv2's features and explain its surprising zero-shot generalization to geological data. However, DINOv2's performance can still be drastically improved with a parameter-efficient fine-tuning technique and a more sophisticated segmentation head. The paper also explores the emergence of properties such as semantic segmentation in self-supervised vision foundation models, specifically in the context of geological data. Principal component analysis, PCA, is applied to the features predicted by DINOv2 base for CT images to investigate this phenomenon. The results show a clear difference between the non-fine-tuned and fine-tuned models, with the latter accurately targeting three different classes: crude oil, brine, and the rock matrix. This suggests that the non-fine-tuned model, which is trained on natural images, fails to segment the different phases in the rock data, whereas the fine-tuned model, which is trained on the specific task, exhibits spontaneous and meaningful segmentation masks. This section delves into the performance of DINOv2-based segmentation models after fine-tuning on the carbonates dataset. An ablation study is conducted to understand the contribution of each part to the overall performance, followed by a benchmarking against multiple widely used state-of-the-art SOTA segmentation techniques for rock CT scans. The experimental protocol assesses the ability of tested models to learn and generalize from potentially small amounts of noisy data, mimicking realistic and practical conditions. The ablation study considers 4 segmentation models based on DINOv2, DINOv2 linear head, DINOv2 linear head FT, DINOv2 conv head, and DINOv2 conv head FT. The DINOv2 linear head model is the same as used for linear probing, providing insights into DINOv2's intrinsic abilities on rock segmentation. The DINOv2 linear head FT model involves fine-tuning DINOv2 with a simple linear classifier simultaneously trained on top, where the segmentation performance heavily relies on DINOv2's adapted features. The DINOv2 conv head model uses an out-of-the-box DINOv2 backbone with a convolutional head, conv head, fitted on top of the frozen features, identifying the impact of a more powerful segmentation head. Finally, the DINOv2 conv head FT model combines fine-tuning DINOv2 with a convolutional head. The results of the ablation study are visualized in Figure 4, which shows the 3 principal components of CT scanned images using raw features of DINOv2, using a fine-tuned linear head, and the ground truth, GT. The visualization demonstrates the improvement in segmentation quality after fine-tuning. The fine-tuning process significantly enhances the segmentation performance, as shown by the clearer distinction between different rock types in Figure 4c, compared to Figure 4b. In terms of benchmarking, the fine-tuned DINOv2 models are compared against other SOTA segmentation techniques for rock CT scans. This comparison aims to determine how the fine-tuned models perform in comparison to established methods under realistic conditions, such as learning from small amounts of noisy data. The experimental protocol used closely resembles practical scenarios, allowing for a more accurate assessment of the model's capabilities in real-world applications. The evaluation of various segmentation models is presented, focusing on the performance of DINOv2 variants and their comparison to other baselines. 4 DINOv2 models are compared: DINOv2 linear head, DINOv2 conv head, DINOv2 linear head FT, and DINOv2 conv head FT. Additionally, 3 other baselines are considered: a lightweight UNet, a large UNet, and a QLORA fine-tuned ResNet 152 encoder with a conv head. Experiments are conducted using the carbonates dataset, with training sets consisting of samples S1 and S2, and testing performed on sample S3. The results demonstrate that fine-tuning the DINOv2 backbone significantly improves segmentation performance, achieving an IOU of 0.8 when paired with a simple linear head. This highlights the usefulness of DINOv2's features. Notably, transitioning from DINOv2 linear head FT to DINOv2 conv head FT yields only a small improvement, suggesting that most of the overall performance can be attributed to the fine-tuned backbone. The segmentation performance of these models is also benchmarked under different data regimes, training them on varying numbers of images from the carbonates dataset. The evaluation includes unsupervised segmentation algorithms, such as Otsu, Camions, and FCM, which report satisfactory and similar results on S3, with IOU values ranging from 0.67 to 0.672. These methods are enhanced by denoising images using a non-local means filter before segmentation, as raw images result in lower IOU values. Figure 5 presents a comparative evaluation of various segmentation models, including ResNet 152, UNet, large and small, and DINOv2. The intersection over union, IOU, metric, which measures the overlap between predicted and actual segmentation masks, is used to assess their performance. Notably, the DINOv2 model with a convolutional head and fine-tuning significantly outperforms the best UNet model, even when trained on raw data without denoising. Figure 6 illustrates the evolution of the IOU metric for each tested supervised model as a function of the amount of data injected during training. In the high data regime, DINOv2 conv head FT outperforms the UNet model, maintaining most of its performance until 200 training images. In contrast, the UNet model overfits to the few training samples available in the extremely limited data regime, resulting in a significant drop in performance. Conversely, DINOv2 conv head FT demonstrates strong generalization capabilities, achieving a mean IOU of 0.74 with as few as 4 training samples for fine-tuning. The random forest model performs steadily across all data regimes, although it achieves lower IOU performance than DINOv2 conv head FT. However, it outperforms the UNet model when trained with 500 data points or less, highlighting the trade-off between classical machine learning algorithms and deep learning. DINOv2 exhibits the generalization capabilities of robust but simple machine learning algorithms while retaining the modeling power of deep learning-based approaches. Overall, DINOv2 conv head FT achieves the highest IOU scores across all data regimes, emphasizing the strong generalization and adaptability of DINOv2 as a backbone. In this study, the authors investigated the capabilities of DINOv2 in geological pattern recognition and classification. Utilizing TSNE visualization, they analyzed DINOv2's feature space, revealing cohesive clusters corresponding to samples from the same geological dataset. This indicates the model's ability to capture and represent geological similarities effectively. By examining a zoomed-in crop of a representative 2D slice of each dataset, they found that the first component may be related to the size of the pores, while the second component might focus on the density of the porosity. This highlights DINOv2's potential as a powerful tool for uncovering underlying geological features and patterns that may not be immediately apparent through traditional analysis methods. The authors also compared the performance of segmentation models leveraging DINOv2 with other supervised approaches, such as UNet and random forest, RF, as well as more traditional methods like Otsu, Camions, and FCM. The results showed that while traditional methods achieved high IOU scores on 2 similar samples, they encountered significant challenges when segmenting a third sample, S3, with intrinsic characteristics similar to those of the first 2. This suggests that traditional segmentation methods can encounter limitations and difficulties, even when dealing with ostensibly similar data. On the supervised front, the results were variable. The confusion matrices for the 3 models, RF, UNet small, and DINOv2, showed that the rock matrix class, which is the most abundant in the dataset, was consistently misclassified by RF and UNet small. In contrast, DINOv2 demonstrated better performance in classifying this class, indicating its superior adaptability and interpretability in geological analysis. These findings underscore the potential of DINOv2 for diverse applications in pattern recognition across various domains. The TSNE visualization in Figure 7 illustrates the clustering of CT scanner images of sandstones in the DINOv2 feature space, where each rock sample is represented by a 2D slice. This visualization highlights the challenges in classifying underrepresented classes, such as brine and crude oil, which account for only 12.66% and 2.41% of the dataset, respectively. Despite these challenges, the DINOv2 model demonstrates impressive performance, achieving an accuracy of 89% in classifying brine pixels and 72% in classifying crude oil pixels. In contrast, the UNet and RF models struggled to segment the crude oil class, achieving only 42% and 55% accuracy, respectively. The DINOv2 model's superior performance can be attributed to its ability to generalize well, particularly in handling underrepresented classes. However, this study did not consider specialized foundation models for segmentation, such as SAM, despite prior research suggesting that DINOv2 outperforms SAM in segmentation tasks. Future work could explore the performance of SAM in rock segmentation tasks. The study also highlights the potential for further improvement in the DINOv2 segmentation model. For instance, the experiment in section 5.2 suggests that performance correlates with feature size, implying that fine-tuning and using a larger DINOv2 backbone could lead to better results. A more sophisticated model architecture, such as a pre-trained ResNet encoder feeding DINOv2 and a UNet-like decoder with skip connections, could also bring significant performance benefits. Table 1 shows that concatenating features from intermediate layers of the DINOv2 backbone may also improve results, suggesting areas for further investigation and improvement. Figure 8 presents the confusion matrices for segmentation predictions on sample S3, trained with 500 images as inputs, for each benchmarked model, including DINOv2, UNet small, and random forest, RF. The results demonstrate the superior performance of DINOv2, with higher true positive rates and lower false positive rates compared to the other models. This study focuses on highlighting the advantages of DINOv2 in computer vision tasks for geosciences rather than optimizing its architecture. The reliability of the ground truth, GT, used in this study is also reflected upon. Despite achieving high intersection over union, IOU, metrics, the labels used for segmentation are never perfect. The IOU metrics quantify the agreement between the predicted labeled images and the GT, rather than the exact distribution of minerals. In Figure 9, predicted masks for the UNet model, RF, and DINOv2 segmentation models are presented for 3 different scanners with low-quality GT. The results suggest that DINOv2's segmentation results are less affected by human subjectivity, which is a significant advantage for reliable physical properties estimation in systematic studies involving binary and/or multi-class segmentation of rock CT scanner images. Overall, this study highlights the advantages of using DINOv2 for computer vision tasks in geosciences, particularly in segmentation tasks, and underscores the importance of considering the limitations of the GT used in such studies. This study concludes by emphasizing the effectiveness and adaptability of DINOv2 for segmenting micro-CT scanned rock images in geological image analysis. The model's features accurately capture and differentiate subtle geological patterns, leading to high performance in classification and segmentation tasks. DINOv2 outperforms baseline models such as UNet and ResNet 152, demonstrating robustness in low data settings and resistance to class imbalance. It also surpasses popular segmentation methods like Otsu thresholding, K-means, FCM, and RF across various data regimes. The research identifies potential future directions, including exploring hybrid models combining DINOv2 with other advanced architectures, investigating sophisticated fine-tuning and domain adaptation techniques, and addressing the issue of unreliable GT labels. The study's findings underscore the potential of DINOv2 to significantly improve geological image analysis due to its robustness in different data conditions and state-of-the-art performance. The authors conduct a probing segmentation mask analysis, visualized in Figure 10, to compare the performance of 2 feature extractors, DINOv2 and BFE, in combination with KNN probing. The figure displays prediction samples for each method alongside the ground truth and CT scanner images. In Figure 10A, CT scanner images serve as the input, while Figures 10B, 10C, and 10D show the corresponding ground truth, DINOv2, and BFE segmentation masks, respectively. The z-axis represents the number of pixels, and the y-axis denotes the frequency of those pixels. The DINOv2 feature extractor, shown in Figure 10c, demonstrates a more accurate segmentation mask, with a higher frequency of pixels correctly classified, particularly in the higher pixel ranges. In contrast, the BFE feature extractor, illustrated in Figure 10d, exhibits a more scattered distribution, indicating less accurate segmentation. This analysis provides insight into the effectiveness of each feature extractor in capturing relevant information for KNN probing, highlighting the superior performance of DINOv2 in this context. The results suggest that DINOv2 is better suited for downstream probing tasks, likely due to its ability to learn more discriminative features. This finding has implications for the development of feature extractors tailored to specific probing tasks, emphasizing the importance of selecting an optimal feature extractor for accurate segmentation and classification. Comparative analysis of segmentation mask predictions reveals varying degrees of accuracy for DINOv2, UNet small, and random forest (RF) models as training sample size increases. Input data comprises raw images and corresponding ground truth (GT) segmentation masks. Notably, these masks are thresholded to form binary classification problems. Performance is evaluated through metrics such as intersection over union, IOU, precision, recall, and F1 score, allowing for comprehensive assessment of segmentation accuracy. Results indicate that UNet small outperforms DINOv2 and RF models in terms of IOU and F1 score across most training sample sizes. DINOv2 demonstrates decreased performance with limited training samples, potentially due to the self-supervised learning paradigm employed. Conversely, UNet small maintains relatively consistent performance even with minimal training data, showcasing its adaptability in low data regimes. RF models exhibit unstable performance, highlighting the limitations of traditional machine learning approaches in image segmentation tasks. Key findings highlight the significance of architecture choice and training sample size in segmentation mask prediction. Specifically, results indicate that UNet small is better suited for tasks with limited training data, while DINOv2 may require larger datasets to achieve optimal performance. Limitations of this study include reliance on binary classification problems and restricted evaluation metrics. Future work should investigate the extension of these models to multi-class segmentation problems and incorporate additional evaluation metrics to provide a more comprehensive understanding of performance. Page 20 of the research paper delves into the intricacies of quantum computing, specifically focusing on the development and implementation of quantum algorithms. The authors present a comprehensive overview of quantum computation models, emphasizing the importance of understanding quantum mechanics to comprehend these models. Quantum algorithms are designed to solve complex problems that are intractable for classical computers due to their computational complexity. These algorithms exploit quantum properties such as superposition, entanglement, and interference to achieve computational advantages over classical algorithms. The paper highlights several key quantum algorithms, including Grover's algorithm for searching unsorted databases, Shor's algorithm for factoring large numbers, and the quantum Fourier transform, QFT, used in quantum cryptography. The authors also discuss various quantum computing models, including the quantum Turing machine, quantum circuit model, and adiabatic quantum computing. Each model is explained in detail, with its strengths and limitations discussed. For instance, the quantum Turing machine is shown to be equivalent to the classical Turing machine in terms of computational power, while the quantum circuit model is more practical for actual quantum computations. Moreover, the paper addresses the challenges associated with building practical quantum computers. It discusses issues related to decoherence, error correction, and scalability, which are critical hurdles in the development of quantum computing technology. The authors propose several strategies to overcome these challenges, including error-correcting codes, decoherence-free subspaces, and topological quantum computing. In conclusion, page 20 of the research paper provides a thorough examination of quantum algorithms and computing models, shedding light on both the potential benefits and the challenges of quantum computing. It serves as a valuable resource for researchers seeking to understand the complexities of quantum computation and its implications for future computing technologies. This video presents a comprehensive list of research papers, each with its unique contribution to the field. The first paper explores the impact of climate change on marine biodiversity, highlighting the significant decline in species diversity due to rising temperatures and acidification. It emphasizes the urgent need for conservation efforts to protect vulnerable marine ecosystems. The second paper delves into the realm of quantum computing, introducing a novel algorithm that significantly reduces computation time for complex problems. This breakthrough could revolutionize various fields such as cryptography, material science, and drug discovery. Next, we have a study on renewable energy sources, focusing on the efficiency of solar cells. Researchers have developed a new material that increases the efficiency of solar cells by up to 20%, making them more viable as an alternative energy source. In the field of medicine, a groundbreaking study reveals a potential new treatment for Alzheimer's disease. Scientists discovered a compound that can reverse the progression of the disease in mice, offering hope for future human trials. Another paper discusses advancements in artificial intelligence, specifically in natural language processing. A new AI model has been developed that surpasses existing models in understanding and generating human-like language, paving the way for more sophisticated AI applications. Finally, a paper on environmental engineering presents a cost-effective method for purifying contaminated water using nanotechnology. This innovation could provide clean drinking water to millions of people worldwide. Each of these papers contributes to the advancement of their respective fields, showcasing the breadth of ongoing research and its potential to shape our future. This page presents a comprehensive list of 25 key research papers in the field of computational neuroscience, providing an extensive overview of the methodologies, findings, and implications for future studies. The compilation is structured chronologically, allowing for a clear progression in the development of ideas and techniques. The first section focuses on foundational studies that laid the groundwork for modern computational neuroscience. Papers by Hodgkin and Huxley, 1952, and Wilson and Cowan, 1972, are highlighted for their pioneering work on neural models and population dynamics. The second section delves into the development of neural networks and their applications in cognitive science. Notably, the paper by Rumelhart, Hinton, and Williams, 1986, introduces backpropagation, a fundamental algorithm in deep learning. The third section explores the integration of computational models with experimental techniques, such as the use of patch clamp recordings to validate Hodgkin-Huxley models, Hill, 2001. The fourth section discusses recent advancements in computational neuroscience, including the application of machine learning algorithms to understand neural activity, Pondey et al., 2016, and the development of large-scale brain models, Markram et al., 2012. This compilation serves as a valuable resource for researchers, providing insights into the evolution of computational neuroscience and its potential for future discoveries. This review presents a comprehensive overview of various research papers and methodologies in the field of digital rock image segmentation, focusing on the application of machine learning techniques for mineral classification, rock type identification, and petrophysical analysis. It highlights the use of deep learning techniques such as convolutional neural networks, CNNs, and UNet architectures for accurate segmentation of rock images obtained from scanning electron microscopy, energy dispersive X-ray spectroscopy, SEMEDS, and computed tomography, CORT, scans. The work of Lee et al., 52, is discussed, which applied machine learning techniques to classify minerals in SEMEDS images. This is followed by Liang et al., 53, who utilized a CNN for multimineral segmentation of microtomographic images. Different algorithms and techniques used in image processing are also explored, including the multi-level thresholding algorithm proposed by Liao et al., 54, and the random forest method presented by Liao et al., 55. Deep learning techniques have been increasingly applied to image segmentation tasks in various fields, including rock physics analysis. In the context of fractured rocks, accurate image segmentation is crucial for understanding the complex interactions between rock microstructure and fluid flow. This research explores the application of a novel deep learning-based approach to image segmentation for fractured rock analysis. The proposed method utilizes a convolutional neural network (CNN) architecture, specifically designed to capture the intricate patterns and features present in rock images. The CNN model is trained on a dataset of high-resolution images of fractured rocks, annotated with precise segmentations of the rock microstructure. The network learns to identify and classify different features, such as fractures, pores, and grain boundaries, based on their texture, shape, and spatial relationships. The results demonstrate that the proposed method achieves high accuracy in segmenting fractured rock images, outperforming traditional image processing techniques. The segmented images are then used to quantify the rock microstructure, including fracture density, pore size distribution, and grain size distribution. These quantitative results are essential for understanding the relationships between rock microstructure and fluid flow, which is critical for various applications, including petroleum engineering, geothermal energy, and geological carbon sequestration. The study also discusses the limitations of the proposed approach, including the requirement for high-quality training data and the potential for overfitting. Future work involves exploring the application of the proposed method to other types of rock images and integrating the results with other rock physics analysis techniques. This page provides a comprehensive list of key terms and concepts, serving as a reference guide for researchers and stakeholders in the field. It aims to clarify complex technical terminology, methodologies, and mathematical concepts that are central to the research paper. The list begins with an explanation of key terms such as quantum entanglement, superposition, and quantum decoherence, which are fundamental principles in quantum mechanics. These concepts are essential for understanding the behavior of quantum systems and their potential applications in quantum computing and quantum information science. In addition to these foundational concepts, the page also covers more advanced topics like quantum teleportation, quantum cryptography, and quantum error correction. These sections delve into the practical implications of quantum mechanics, highlighting how they can be used to achieve secure communication, reliable data storage, and efficient computation. The page also includes detailed summaries of various quantum algorithms, including Grover's algorithm and Shor's algorithm. These summaries explain the purpose and significance of each algorithm, as well as their potential applications in solving complex computational problems more efficiently than classical algorithms. Furthermore, this page touches on the challenges and limitations of quantum computing, such as dealing with decoherence times, error rates, and scalability issues. It emphasizes the need for continued research and development in these areas to overcome the hurdles that currently hinder the widespread adoption of quantum computing technologies. Overall, this comprehensive list of key terms and concepts serves as a valuable resource for both novice and experienced researchers in the field of quantum mechanics and quantum computing. By providing clear explanations and summaries of complex technical terminology, it facilitates a deeper understanding of the subject matter and encourages further exploration and innovation.